Hey everyone, my name is Hans Mohrmann. I'm the lead geospatial data engineer at Brightband, and I'm really excited to present some of our work with you today. So I'm going to talk about observational weather data. I'm going to start with some of the motivation for this work from the machine learning weather forecasting world, and then I'll walk you through what we're doing to make what we think is some really valuable data a lot more accessible. And also, this work has been done as part of a cooperative research agreement with NOAA, and so particular thanks to Sergey Frolov from NOAA for his from NOAA PSL for his support. Okay, first off, some intros. What's Brightband? So we're a public benefit corporation. We started last year with the goal of making AI weather forecasting tools more broadly available. And we're a small team, only 6 people full time. So when I said I'm the lead geospatial data engineer, I'm the only one. Yeah. And aside from the work that I'm presenting today, we also have some work we're doing on building our own observation-based weather forecasting systems, as well as some benchmarking tools around model intercomparison for extreme weather. So if you care about those two things, come find me in the break or tonight. So yeah, the last 4 years have been super exciting for weather forecasting world. We've experienced this sort of explosion of skillful AI and machine learning weather forecasting models. So if you saw Alex Morose's great talk this morning, this plot will be very familiar. It's a figure I really love from Stefan Rasp at Google DeepMind, and it shows the progression of skill relative to IFS HRES, which is sort of the European model, the gold standard for medium-range weather forecasting. And so what we're seeing here is that for some metrics, in this case for the 3-day 850 millibar temperature RMSE, these AI models are actually outperforming the classic physics-based models. So like things that are kind of above the line here. So like all this stuff is like outperforming our best-in-class physics-based models. And more recently, there's been this sort of new set of models that have emerged and that are really interesting. So these ones in the bottom right here. So Aardvark, GraphDP, and Fuji weather. And I'm just going to pull out 2 of these here. So why are these models interesting? They work a little differently from the other AI models, and that's that they're driven directly from observations. So this is this is really cool. Maybe to kind of explain like how this works and what this means, we can take a step back and just look at how we make a weather forecast. So up top here, you've got like traditional numerical weather prediction, and it looks like this. You get some observations, from satellites, from ground stations, from airplanes and balloons and whatever. You use a data assimilation system to do a few things. You mush these all together. You combine them with like a background state. You reconcile errors, and then you provide a best guess at a global gridded, physically consistent state, sort of analysis state of the current state here. And then the second thing is that you step that forward in time with your forecast model, like IFS or GFS. And both the data assimilation and the forecasting are both like really complex processes, complex models. They're computationally intensive, and so they've really both been done by large organizations like the ECMWF and NOAA. And I should just say here to be clear up top, NOAA does a lot of things across science, and all of the work here, including all these models, even the bottom ones, aren't possible without NOAA. So yeah, that should be said. But yeah, so the first kind of big paradigm shift here that we saw from these AI models like GraphCast, they've sort of replaced the physics, the forecasting model here. And this has democratized the ability to make a forecast. Running GraphCast is easier than running GFS. It's still not super easy, but it's a lot easier and cheaper. But the problem is that you're still initializing off of the analysis state that's being produced by NOAA or the ECMWF, and so you're still sort of dependent on these organizations to deal with your observations. These more recent observation-driven models can run directly from the observations, and there's no need for relying on this data assimilation process to sort of create your analysis state. So was that interesting? Well, for one thing, pretty much every AI model is trained off of the same data set, off of ERA5, which is a historical reanalysis of the world. It's sort of this, this global gridded state using all available observations going back decades and decades and decades. And it's a really amazing data set, and all of the breakthroughs we've seen on sort of that step have been enabled by having sort of this ARCO analysis-ready cloud-optimized copy of ERA5 in ZAR. So there you go. Thanks to Alex for making that. But there's a sort of a few limitations that this gives here. So one thing you have is that it limits the flexibility of the models that you train off of it. They need inputs that look like ERA5. And then any problems that ERA5 has in representing the world will also likely be baked into these models in some way. Observation-driven models, at the bottom row here, don't intrinsically have these limitations. They need inputs that look like what they're trained off of, so they just need the observations directly. and then they can run as soon as these observations are available. So there's no need for like a data assimilation cycle to finish. They do have a slightly different problem though, which is that they are a hassle to train. There's no like obvious Era 5 like equivalent collection of observations to sort of to train them off of. And so, we could look at what's been used maybe by these data assimilation models themselves to run off of for the last few decades and consider that as a place to draw from. But I don't know if you guys saw it when I skipped just now, but who here knows what the preferred format is for observational weather data for operational forecasting? BUFR. Yeah, this guy knows. It's not GRIB. GRIB would be nice. It's the preferred output. Yeah, no. Yeah. So for inputs, it's all in BUFR. And I'm going to talk a lot more about BUFR in the talk, but it's if you're not familiar with it, it's like the fax machine of data formats. It's from the 80s. It's hard to work with. And so yeah, kind of summarizing a lot of that, if you're trying to find a good collection of data to sort of start training your observation-based machine learning weather prediction models, there's a lot of challenges here. And I saw in Sarah's talk as well, like looks like for flood modeling, you have similar problems. Like you have different grids, you have different sources of data, you have different shapes of data. Some are trajectories. If you're working with radial occultation, it's a really weird shape. You got different formats and standards and licenses. And so yeah, this is like a big barrier to doing this type of modeling here. And there are some great platforms like Google Earth Engine and Planetary Computer that have big collections of data, but they're not really one-stop shops for all of the data you care about for weather forecasting. But there does exist this really cool NOAA-NASA initiative here, the Joint Archive of Observations, the NNJA Archive. It's a great name. This is basically just the entire history of all input data that we've used for weather modeling operationally. It's just like literally what we fed into the data assimilation models to generate all of the actual forecasts we've had over the last years and decades of making these things. And it really is meant to be used for improving reanalysis, and it's got these great properties to it. It's a single, one archive. It's got good documentation. It's published on S3. It's got permissive license. And the critical thing is that it's meant to be the data that's useful for this type of work. It's the data that we care about for weather forecasting. It's got this really big kind of problem here, which is that it's in BUFR. And this is the sort of Wikipedia definition, or this is on the Wikipedia for BUFR. It's just a hard format to use. This isn't NOAA's fault. This is the archive that they had. They just literally published their archive of data. But yeah, so it's good in that it's self-describing. You can read a BUFR table and kind of figure out what's in there. But there's big problems with it. It's got these ugly kind of arbitrary nested structs in it. There's no way to unpack them without lots of custom logic. There's a divide in the standard between NOAA and ECMWF. The tools are all legacy Fortran libraries to read it. So it's about as far away from being cloud native as you could possibly be while still being in an S3 bucket. And if anybody ever writes a virtualized R for BUFR, I will actually eat my hat, Tom. It's just impossible. So yeah, so summarizing where we're at so far, we'd like this multi-sensor, big, rich collection of weather observations for observation-driven machine learning weather prediction. The NNJA Archive seems to have the right data, but it's in BUFR. So the solution here is just to debuffer NNJA. And the rest of the talk is just me describing kind of how we did that and then how we're serving it all up. So this is our pipeline for a thing we're calling NNJA. It's an even better name. And so what we want to do is kind of convert these BUFR files to something that's more useful and consumable by people. So these are the steps we're following here. The first thing we do is we sort of debuffer them to some intermediate format that's kind of an easy target to save this data to. And then we have the second step where we have a sort of more opinionated processing to reshape this data a little bit and serve it up in a way that's easily consumable by people. And then this sort of final step here is what you would do if you were using this data. We do this internally ourselves for our own machine learning models, but that's picking and choosing from the AI-ready archive to sort of use what you want to do for training. So some debuffering here. This is just some more BUFR data, what it looks like. You've got these tables, at least in NOAA BUFR files, you have these sort of BUFR tables that describe what's in the file. And you have this sort of binary packed data with these mnemonics in it. And looking at this, you're not really sure how to deal with it. But if you just sort of expand it out, and you can reshape a BUFR file to kind of look like a kind of a tree view here. And if you look at this, looks a little friendlier, right? You're okay, I kind of see if I have data that looks like this. I could say this is a JSON or something. This is a sort of familiar looking shape of data. What we do instead is we save it to Apache Avro. So this is that same data, but as like an Avro schema here. And Avro it's a modern format. It's like a record-based format, and so it's kind of pretty one-to-one with what's in the buffer data. Yeah, it's a good target, and like the good thing about Avro is that there's lots of tools to read and write Avro data. So like once you have your data in Avro, you can kind of work with it there. So. But for all of its problems, or all its sort of conveniences, Avro has some problems for like serving data, which is that, for one thing, not all sort of data science, machine learning tools know how to read Avro. I'm guessing not a lot of people in this room work with Avro data. I'm sure some people do, but like, it's not super common. It doesn't compress well, because it has this sort of like record-based structure. The Avro files are actually like much bigger than the buffer files. It's about 3 times the size of the buffer data. And then, crucially, if you want to like just access one part of your Avro data, like you just want to have, the radiances from one satellite channel or something, you have to kind of parse through the entire record. So you can't like easily just pick the bits of it that you want. So what we saw in Tom's talk this morning, like for AI, ML applications, like you want to be able to not be I/O bound. You want to be able to stream just what you care about into memory as fast as possible. And so Avro kind of sucks for that. But what people do like is Parquets. So yeah, Sarah, not using ZAR here. I can talk about that more later. But people like Parquets. We've talked about them a lot the last couple of days. So what we do with our Avro files is we then convert them to Parquets. And they've got broad compatibility. Most people know how to read a Parquet file. You can drill down really easily and subset by different columns or partitions your Parquet data. So yeah, that's what we sort of like decide to use to serve this data here. And so what we're doing here is we have one like Parquet file, or I'll just partition, but like one schema per sensor. So like the balloon data and the satellite, like infrared data are not, like they have different sets of columns in them. We do some standardization. So like, we have like a timestamp and a latitude and a longitude for everything. So you can like easily subset that way. We consolidate to daily partitions. So the Avro files, just like the buffer files, have these sort of like 6 hourly partitions. We just make them daily partitions. And then we do this thing where we kind of flatten out the struct columns in our Parquet. So like a Parquet can have a column that has, like an array in it. That's totally fine. But what we found is that actually lots of tools that read Parquets in the cloud don't do a good job sort of drilling down and just accessing some part of that. So like if you have, 10 different satellite radiances in a column, and you just want to have one of them, again, you kind of have to load that entire column. So what we do is we just make it 10 columns. And then basically every tool can just subset just that one radiance column that you care about. There's a downside here, which is that we end up with lots and lots of columns. But the good thing about Parquets is that you just kind of grab the columns you care about. So yeah, that kind of solves the problem of like accessibility. Like once this data is in Parquet, it's easy to kind of load what you care about. There's still some problems of explorability, which is that we now have like lots of columns of data. And so we just built a little lightweight Python SDK on top of it that just kind of helps with exploring the data a little bit. So you can kind of like list to see what catalog, what data sets we have in the catalog, and then you can load that, and then you can sort of like, list out the variables, and there's some metadata on the variables, and you can subset by variables and subset by time, and kind of whatever point you want, you can drop down and just like load this like a pandas or a polars or a Dask data frame, and then do what you want with that, right? So this is just kind of meant to help you find the data you care about. And then there's some like, this is all published on GitHub, and there's some notebooks as well on there. So yeah, that hopefully helps with like exploring the data a little bit. So what's currently available? We've had this preview release. It's been out now for a few months. And this is sort of the core set of initial data sets we've been working with. So there's like some low Earth orbit microwave and infrared data sets, and some geostationary data sets, and then like some weather balloons and sort of weather stations. And then, just kind of emphasize, like, these contain all of the data that's in the buffer files. So, like, and the satellites, you might have, like, hundreds of channels. For surface stations, you have whatever, like, weird, like, variables they decided to report. Like, airports might report visibility or so. That's, like, all somewhere buried in this archive, and a little easier to get to now. For the weather balloons, we have full profiles. So we have, like, all sort of significant levels if you care about radiosonde data, and then it's published for 4 years and openly licensed, just like the NNJA data that's built on top of. And it's just, you can just access the raw data as well. Like, you don't need to use our SDK. You could just go to that bucket and just read that Parquet file however you like, and there it is. And then that's where we have the Python SDK as well. So. And this is just a great way to like play with this data. Like, suddenly it's pretty easy to just load anything you care about that might be useful for weather forecasting here. So like here we're seeing 3 hours of data for a bunch of different satellite data sets and some surface station data and whatever. And this is like a few lines of Python now. You just kind of load the data sets in subset, and then you plot it with matplotlib, and there you go. Yeah, and I didn't do like a live demo, but this takes like however long it takes to just read Parquet files from S3. So it's very fast. It's seconds. Yeah, and then joining the group of people here who had hoped to have this done before the conference, but are running a little over. So very soon we'll have our V1 release. It's just the same data sets, but they're full history. So going back however far, they're in the NNJA Archive. So for some of these, that's like a lot of data. Yeah, and we also have some SDK updates and bug fixes there. Next steps for this project, we're trying to move to multi-cloud, get this in the AWS Open Data Program, get this into the NOAA Nod program, add more data sets. We're currently working with aircraft and radial occultation data, which is really interesting. And then, yeah, just add more to the SDK, lots to do there. So what we really want, though, is for people to try this out and play with it and see if it's valuable to them. We're finding a lot of value in it ourselves for our own internal ML training. And we just think it's an underutilized resource, and hopefully people find some value in it. So we've made a lot of choices in how we're processing and serving things. If you're looking at this, you're like, oh, this is great, but I kind of need this in BigQuery. I want to be able to do some geo subsetting or something a little different. Just come talk to me, and we've got a lot of things in the roadmap, but we can prioritize based on what people find most helpful. So yeah, that's it. I'll take questions.
This is all archival data.
Yeah.
Right? But presumably new observations are being taken every second.
Yeah.
Do those also come in BUFR? Is there somewhere that you can watch them come in and add I can make a real-time version of this?
They're published. Both NOAA and ESMA have published them as well, so there are real-time feeds for those as well. The archive itself has a couple days lag on it. There's a bit of a nuance around non-commercial data sets. So some things that are in this are like aircraft data, for instance. You can have that. NOAA can publish it after a couple of days. They can't publish it immediately. So there's stuff in here that doesn't exist in the real-time feeds, but for the most part, yeah, there is real-time equivalents to this as well. And if you want to use that, come talk to us. That's kind of what we're into. So yeah.
It's not so much on the specifics of BUFR.
Sorry.
Oh.
Do you mind going to the mic?
Oh, sure. This isn't about the specifics of BUFR necessarily or any of those file formats, but thinking more generally about OBS to OBS and then comparing to all the Era 5 models, like that initial plot you show.
Yeah.
How is that actually an apples to apples comparison? And how do you think about evaluating these relative to all the Era 5 based models?
Yeah, so this is a great question for Stefan Rasp, who has put all these numbers in here. But some of these models do produce gridded outputs as well. So you just literally do have the exact same fields that you can validate against. If you're just literally producing weather station output, then yeah, you can't compare to 850 millibar temperatures. But I'm not sure if there's different ways to do that. I think for most of these though, there's a kind of the way that we're working with it too. We produce a gridded state that looks like the output from weather model. So at that point, it's just a direct comparison.
Sorry, I should have stayed up here. So you're producing a gridded state output from direct OBS as inputs?
In our case, yeah.
Cool.
But yeah, that's not
Super cool.
Yeah, different teams take different approaches. That's what we're doing. So yeah. All right. Cool. Well, thanks everyone.